the second compensator is lag compensator. So what is the transfer function of lag compensator? So we can write it as a GC of S is equal to S plus 1 by tau over, we have S plus 1 by beta tau. So here I am taking the beta constant where the beta is greater than 1 and tau also of course it is greater than 0. So when you look at poles and zeros in S plane, my S plane poles and 0 like this, we have a finite pole and finite 0. Now to the nearer to the imaginary, in this case we will be having a pole, so the pole is minus 1 by beta tau, where the 0 is away from the imaginary axis, that is minus 1 by tau. Since the pole is nearer to the imaginary, then we can call that particular compensator is lag compensator. So whenever you are given any compensator transfer function, if you want to know whether it is a lead compensator or lag compensator, just locate the poles and zeros on S plane and see which one is nearer. If 0 is nearer to the imaginary, then we say it is a lead compensator. If the pole is nearer to the imaginary, then we say it is lag compensator. But because the effect of pole is always lag, so pole gives the negative values of phase lags and 0 gives the positive values of the phase. Now, so with this poles and zeros, we can say pole is nearer to the imaginary axis. Now, how can we realize the lag compensator using the resistors and capacitors? Now, as usual, here I have R1 and R2 in this particular resistive network. Again, I have the capacitor. Now, the capacitor is placed in this particular branch and it is connected in series with the R2. So, when you compare with the lead network where this capacitor was parallel to the R1. Now, so we can easily find the transfer function V0 of S by Vi of S, Z2 divided by Z1 plus Z2, where Z2 is R2 plus 1 by Cs, which is the series combination of resistor and capacitors, and Z1 is R1. Then if we substitute and we compare with that, then you will be getting it as we have GC of S, numerator will be getting 1 plus R2C2S over we have R1 plus R2 by R2 and R2CS plus 1. So this factor, that is which is R1 plus R2 by R2, we can take it as beta, and we have again R2C which we can take it as tau, and we can write the transfer function as GC of S is equal to 1 plus tau S divided by 1 plus beta tau S, where tau is R2C and beta is R1 plus R2 by R2. Since R1 plus R2 by R2 is obviously greater than 1, the beta is always greater than 1. Then in this case the amplifier is not needed because output is not going to be attenuated. So this is one of the advantage of the lag compensator when compared with the counterpart lead compensator. Now, so substitute S is equal to j omega, you have GC of j omega, we can write numerator 1 plus j tau omega divided by I have 1 plus j, you have beta tau omega. Now, when you draw the frequency response, again it is a type 0 system. Initially we have 0 dB for decade. There are two corner frequencies. The first corner frequency is 1 by beta tau and the next is 1 by tau. Since this is a pole, then we have minus 20 dB for decade. Then again we have, there is a 0, therefore plus 20, minus 20 plus 20, it is going to be 0 dB for decade. We will get line like this. So this is the magnitude. What will be the phase? Again, the phase starting is 0, ending is also 0, but in between we have negative values of phase angles. And as I said, we want where this maximum is occurring. The maximum phase angle is phi m and it is occurring at omega m. And what will be the value of the magnitude in this case? It is 10 log 1 by alpha. So in steady conditions, the output of the lag network is with the input, when you compare it lags with the network. So what will be the maximum phase angle? The maximum phase angle you can obtain very easily. The phi m is equal to beta minus 1 by beta plus 1. The derivation of this will be just similar to the derivation of the lead compensator. So only thing is here the sin phi m will be getting beta minus 1 by beta plus m. And corresponding frequency omega m is going to be again same. It is a geometric mean of two corner frequencies. Therefore it results in 1 by tau root beta. And what are the effects of a lag compensator? So basically lag compensator is a low pass filter, hence the noise is easily filtered. Therefore signals to noise ratio is improved in the case of the lag compensator. Similarly, lag compensator improves the steady state performance. That means it improves the accuracy of the system. it nullifies or it decreases the steady state error, and lag compensator effect will be similar to PI controller. Then what are the drawbacks with the lag compensator? Now the first drawback is the bandwidth will be very low, therefore the transient response will be very poor, we can say, or it cannot be used to improve the transient response of system because it gives very small bandwidth value. And similarly, if the bandwidth is very low, obviously rise term will be more. And since we are introducing the pole which is nearer to the imaginary, there will be effect of relative stability of the system. We can say relative stability may be affected when you use the lag compensator. Similarly, with the help of the lag compensator, system may become more sensitive to the parameter variations. Now these are some of the advantages and disadvantages of the lag compensators. Now the third compensator is lag lead compensator. The transfer function of this compensator goes like this. Your GC of S is equal to, in the numerator we have two terms, S plus 1 by tau into S plus 1 by tau 2, S plus 1 by tau 1, S plus 1 by tau 2. The denominator we have S plus 1 by beta tau 1 into S plus beta by tau 2. So we have tau 1, tau 2, and with the help of these two, then I can have my poles and zeros in this particular compensator. When you locate these poles and zeros here, you know the name of it, it is a lag lead compensator, which means, which is always with respect to the imaginary axis. If the imaginary axis, the lag is nearer and the lead is away from it, then it becomes the lag lead compensator. As I said, there is a fourth compensator is also available, lead lag compensator. In that case, so lead will be the nearer to the imaginary and the lag is away from the imaginary. Now, so in this case, lag lead compensator, therefore the lag will be nearer to the imaginary. What will be the lag again? In lag, one finite pole, one finite zero. So in that the finite pole is nearer, and then after that I have finite zero. Then followed by lead. So in lead again we have zero is towards the right side and pole is away from it. So overall, if you look at so the rightmost end we have pole and leftmost end we have pole, in between we have two zeros, which is a lag lead compensator pole zero diagram. And what are the corresponding locations? So I have pole, that is 1 by minus 1 by beta tau 1, and we have 0 minus 1 by tau 1 and minus 1 by tau 2, and the last we have minus 1 by beta minus beta by tau 2. So this is my pole 0 and this is my transfer function of lag lead compensator. Now we will see how to realize using RC network that lag lead compensator. So in this network we have two resistors R1, R2 and two capacitors C1 and C2. So R1, C1 we have parallel combination which is responsible for the lead compensator, and R2, C2 is the series combination responsible for the lag compensator. And we can the output voltage and input voltage, then we can find out the ratio V2 of S by Vn of S. So we have, this is Z1, this is Z2. So Z2 by Z1 we can write it very easily, then we can rearrange the terms, then we will be getting it as we have GC of S, the big equation, V2 by V1 or V2 of S by V1 of S is equal to, the numerator we have S plus 1 by R1 C1 and into S plus 1 by R2 C2. The denominator we have S square term because it's a second order term, and we have one big term here, that is a 1 by R1 C1 plus 1 by R2 C2 plus 1 by R2 C1 into S plus I have the last term 1 by R1 R2 C1 C2. Now by taking this transfer function, comparing with that, we can easily result, we can write the things as tau 1 is R1 C1 and tau 2 is R2 C2, and we can also write the middle term as 1 by R1 C1 plus 1 by R2 C2 plus 1 by R2 C1 is equal to 1 by beta tau 1 plus 1 by alpha tau 2, and alpha beta is equal to 1, that we know. Therefore the last term we can change it as beta by tau 2, and also we can write R1 R2 C1 C2 as alpha beta tau 1 tau 2. Therefore when you look at the original transfer function, when you compare it, then we'll be getting it as a GC of S. We know it is S plus 1 by tau 1, S plus 1 by tau 2. In the denominator we have S plus 1 by beta tau 1 plus S plus beta by tau 2. We know that beta is greater than 1. And what are the things that when you compare tau 1, tau 2, we know already tau 1 is R1C1, tau 2 is R2C2, and 1 by R1C1 plus 1 by R2C2 plus 1 by R2C1 is 1 by beta tau 1 plus beta by tau 2. Now, so with this transfer function pole zero locations, then we can draw the frequency response of the system. The frequency response look like this, and there are 4 corner frequencies. When you write in increasing order, that is going to be 1 by beta tau 1 and 1 by tau 1, 1 by tau 2 and 1 by beta by tau 2. So these are the 4 corner frequencies we have. So with these frequencies, then we can draw the magnitude diagram. So it is a type 0 system, therefore initially it is coming with the 0 dB for decade. Now at first corner frequency it is pole, therefore we have minus 20 dB for decade. There is a slope which is coming down. Then again there is a 0, therefore it compensated, we will get 0 dB for decade. Again there is a 0, we will get plus 20 dB for decade. Again there is a pole, therefore it is 0 dB for decade. So this is my the magnitude diagram. Similarly, I can draw the phase plot. Again the starting is 0, ending is also 0, but in between how it is varying. So we have the first lag effect, therefore it goes down and again it increases, and beyond 0 again it increases, and again it goes back to the 0. So this is what we have the phase plot for lag lead compensator. Then we can easily look at what is the phase lag we want at what frequency, and what is the phase maximum lead at what frequency. We can easily derive things. Now in this case we are using the effect of both lag and lead. Therefore what are the effects of lag lead compensator? So it improves both the transient behavior of the system as well as the your steady state behavior of the system. It improves the bandwidth, and also it improves the signal to noise ratio.